start, I just quickly go through what we did last week. So mainly last week, we discussed the assembly of multiple elements. Just put this a little bit more. Yeah. So last week, we discussed mainly the assembly of elements. So we developed the first element. We have the stiffness matrix for the first element. And then we want to discuss a situation where you have multiple elements. So for example, you have a case where you have a load at the mid-length. Then in this case, you need to have multiple elements. So this can be element number 1. This can be element number 2. And then on the global level, for the whole problem, we have 1, 2, and 3 nodes. And this would result into a system that is composed of 3 rows and 3 columns. So this is 1, 2, and 3, 1, 2, and 3. And to start with, we said that the system is composed of zeros, so you have zeros pretty much everywhere. Now, for each one of these elements, so let us say that this is element number 1 and this is element number 2. We have 2 nodes. This is node 1 and this is node 2. Again, node number 1 and node number 2. And we have a stiffness matrix, and we want to find the relation between the stiffness matrix of this element and the big one, and the same for the second element. So we write down the stiffness matrix for the first element. This is EA over L minus 1, 1, sorry, plus 1, minus 1, minus 1, and plus 1. And this is for element number 1. And the same is true for element number 2. I mean, whatever we have for EA, we put that in there. So it is 1, minus 1, minus 1, and 1. And this is node number 1, node number 2, 1, and 2. The same is correct here, 1, and 2, 1, and 2. Now we need to find the connection. The connection would happen through the relation between the local nodes, the element nodes, and the global nodes. So this node, number 1 for element number 1, obviously this is element number 2. So this node is connected to node number 1. So I'm just going to write 1 here. And this one is connected to node number 2. So this would be 2. Again, this is correct for the same, for the same logic, you can apply the same concept to the rows. If you look into the second element, now this is the second element. The first node is connected to node number 2. And the third one, or the second one, is connected to node number 3. So it is 2, 3, and 2, 3. Now the assembly of the system is just reduced to only reading coordinates and adding them into the system. So this one, this entry here, 1, 1, will get into here. So this will be 1. And since we have 0 in there, we add 1 to 0. So the final product is going to be 1. This is 2, 1. So you look into 2, 1. So this is 2, 1. You add, or in this case, you subtract 1. And then you have 1 here and minus 1 here. If you look into the second element, the first entry is here. So it is 2 and 2. So this should be here, 2 and 2. Since you already have added 1 and you add another 1, so this whole thing will become 2 and so on. So this is mainly what we discussed last week. Before we get into this, I want to discuss something relatively an old concept. Now, I'm going to go back a little bit in history. I'm going to talk about a specific experiment which I think has fundamentally affected physics as we understand it, and later on engineering. So there was an experiment done by Hooke. I mean, there's a very, very famous law in physics called Hooke's law. I'm sure you have seen that in elementary physics, but I'm going to quickly talk about it, and later on you'll see the relation to the finite element methods. Now, Hooke brought a spring, fixed one end, and applied a force at this free end, and then he measured the displacement resulting from the force. Now, he did the experiment for multiple forces and multiple displacement. He found that for a force F1, this is F and this is displacement. For a force F1, you get this point. So you get a displacement of U1. For a force F2, you have a displacement U2, and so on. And he observed that all these points, as long as you don't break the spring, you'll see that all the nodes will happen on a line. Now, if you want to generalize the concept, instead of using one spring, you use a free end on both sides, and you have a force F1 and F2 and U1 and U2. Now, you can do the same thing for both forces. If you take, first of all, force F1, so F1 would be equal. All right, so I probably just explain a little bit about this figure here before we get into the generalized case. If you look into this line, you'll see that all the forces and all the displacements are linked. And the relation between them is F equal to some stiffness, some constant has to do with the spring, and this is constant for a specific spring, with the displacement. And this is constant, so the relation is linear, and this would define linear behavior of structures as we know them. Now, if you want to generalize this, you can do the same thing for force F1. So K will be U1 minus U2 in this case, and F2 will be K multiplied by U2 minus U1. Now, of course, these two forces are coupled, so there will be an equilibrium between both, and this equilibrium will be connected through the displacement, and you can write this in a general form in this way. So you can write it F1, F2 is equal to K minus K minus K and K. I'm just going to remove this here, multiplied with U1 and U2. Well, this is just the same equations written in matrix form. Now, if you look into this one, you would remember that this is very similar to this stiffness matrix. In fact, if you just take the K to the outside, you'll have 1, minus 1, minus 1, and 1, multiplied with U1 and U2 is equal to F1 and F2. So this is pretty much exactly the same behavior for the bar. For the bar problem we had earlier, you have a fixed end, and then you have a cross-section and elasticity modulus and length, and the stiffness of this bar will be the elasticity modulus multiplied by the cross-section divided by L. So this constant for the bar will behave exactly like the constant of the spring. So we brought the finite element from this origin, so that if you go back to the origin of the finite element method, it goes all the way back to this Hooke's law. And based on Hooke's law, we develop what is called later the stiffness method, the direct stiffness method, and then the direct stiffness method resulted into the finite element method. And in some way, we have extended the concept using the finite element method. We have extended the concept into any number of dimensions. So instead of having springs that work in one dimension, we went into creating springs that work in 2 dimensions. We can create also rotational springs if you look into beams, and we can do the same thing in 3 dimensions. And we designed the whole engineering concept of all the engineering structures you have around you are to an extent based on springs. So we describe them just like springs that are active in 1 dimension, 2 dimensions, and 3 dimensions. And because these springs, they have this linear relation between the force and the displacement, the entire designs we work with, or the majority of the designs, are called linear designs. Now, if this relation is not linear, if this relation is quadratic or cubic, then in this case, we move into a nonlinear situation, and this will fundamentally change everything you have worked on so far. So far you have only been working on linear structures. So if we move into a nonlinear structure, this is going to be quite complex, and you cannot use it with, you cannot do much on that with the standard engineering techniques that you have learned so far. So we have to move into the nonlinear finite element, which is something I'll probably discuss in the 2nd semester of year 5. All right. Now, if you want to push this idea further and have just create an assembly of springs, you can also do that, and you do it exactly the same way like we have done for bars. So you have two springs, for example, you have forces applied to them. So this is F1, this is F2, and this is F3. And then you have node 1, node 2, and node 3. If you take the equilibrium for the first spring, I'm just going to write the equations here. F1 is equal to K. For the first spring, we have K1. For the second spring, we have K2. But I'm just going to assume that K1 is equal to K2. I'm calling it K. We have U2 minus U1. For the first one, we also have F2. Now, F2, some part of it will be active on the first spring, and some part will be active on the second spring. At the moment, we don't know which one is active on which one. So I'm just going to add 1 to this F2 here, which is coming from the first spring. And we have this is meant to be U1, since we have the force. Since we have the force F1, this is meant to be U1 minus U2. And then this one is going to be U2 minus U1. This is all coming from the first spring. The second spring here, we have F2. And then this is F2 because it is coming from the second part, is equal to K multiplied with U2 minus U3. And if you look into the last node here and the last force, so F3 is equal to K multiplied by U3 minus U2. Now, I can add these two equations to have F2. So these two added together will be F2 equal to F2 1 plus F2 2. So adding both parts will result into F2, and then I can add up whatever I have in these brackets. I'm just going to take K to the outside and add what I have inside the bracket. So it is U2 minus U1 plus U2 minus U3. So it is U2 minus U1 plus U2 minus U3. Or you just can write it in this way. It's K multiplied by minus U1 plus 2U2 minus U3. And then you have the third equation. So this is equation number 1. This is equation number 2. And this is equation number. So this is F2, and this is equation number 3. Now I'm just going to write the three equations together. So I have F1 is equal to K multiplied by U1 minus U2. I have F2 is equal to K multiplied by minus U1 plus 2U2 minus U3. And then I have F3 is equal to K multiplied by U3 minus U2. Now, if you want to write down this in matrix form, you will have, F1, F2, and F3 is equal to K. This is a common factor multiplied by something, multiplied by the displacement. It is U1, U2, and U3. And then in the first equation, you have U1 plus and U2 minus, and you don't have U3. So I'm just going to write 1, minus 1, and 0. In the second equation, you have minus U1, 2U2, and minus U3. So it is minus 1, 2, and minus 1. And if you look into the third equation, you have minus U2 plus U3, and you don't have U1. So it is going to be minus 1 and 1. Now, again, if you look into this system here, this looks exactly like, look into the springs. Look into what we have here. Eventually here we have 1, minus 1, minus 1, 2. And then if you continue the assembly, you have minus 1, minus 1 here, minus 1, and 1 here. So this is basically pretty much the same concept, but applied to springs. And if you look into the finite element method, the linear finite element method, will be treating the entire universe as springs that can rotate or can move in 2 dimensions or 3 dimensions. So this is pretty much it is. It is the finite element method. So right, the linear finite element method. All right, so do you have any questions before I continue? All right, so Jacob is asking what dictates U if it is positive or negative. It is a sign convention, all right? See, you assume that F1 is moving in this direction, U1 is moving in this direction, and U2 is moving in this direction. So the 3 of them are moving in one direction. Now U1 will need to be subtracted from U2 in order to identify how much the spring is compressed in order to identify the value of F. So F is related to the contraction of the spring. And if you want to add the displacement together, this is not going to work, is going to result into, I mean, the difference between U1 and U2 is basically the amount the spring is compressed. So the sign convention is completely up to you. I could have assumed that F1 is moving in a different direction and U1 and U2 are moving in different directions. I just need to be consistent in my assumptions. I would suggest if you want to try it on a different set of assumptions, but be consistent throughout, and then you are going to get exactly the same results eventually. And Singh is asking F1, 2 and F21. What do you mean with F1, 2? Do you mean F2 from the first spring and F2 from the second spring? I don't know what you mean with F1, 2 or 2, 1. All right, the split of F2. All right. Okay, so F2, I have the value of F2 coming from one spring or the other spring. Sorry. Yeah, here. So F2, for the time being, I assume that you don't know F2. I probably just use the highlighter. This way you probably can see it better. So F2 is going to be active on the first spring and is going to be active on the second spring. Now, what is the proportion of F2 active on the second spring and what is the proportion of F2 active on this first spring? This is something you don't know. So this is why you assume that some proportion of F2 is active on the first spring, and you call that F21. And some proportion of F2 is active on the second spring, and you call this proportion F22. All right. Now, you don't know them, so you just keep them unknown, and you don't care about the values for the time being, because eventually you are going to add them together and get F2 back. All right. So you just get F2 back, and you know the value of F2. So the split would happen in this way. Now, once you get into adding them together, then in this case, you know the value of F2. Now, probably if you think about it, you would see that the value of the proportion of F2 that is going to go into the first spring or the proportion that is going to go into the second spring is much related to the stiffness of the spring. So the stronger the spring, the more of F2 is going to observe. Now, since K1 and K2 are equal, you can expect that proportion is going to go equally into both springs. All right, so I'm going to solve now one example using these springs, and I'm going to solve it first using my own convention of numbering, and then I'm going to ask you to solve it again using a second convention of numbering. Now, this is an exercise for you to work on the assembly. What I care about at this stage is mainly the assembly, that you understand correctly. So let us have 3 springs. The stiffness of the first spring is 1000. is 2000 and 3000 for the last spring. You have one force that is active at this node between the second and the third spring, and the springs are fixed at both ends. So at this end, the springs, or this assembly of springs, is fixed, and this same is correct here. Now I'm going to solve this using the finite element method. I want you to, for the time being, ignore these numbers for the nodes. So I'm going to assume that this is node number 1, this is node number 2, this is node number 3, and this is node number 4. All right. I probably just used the red color since I've been using red color for the global numbering. I'm just going to use the same convention here. So I have node number 1, node number 2, node number 3, and node number 4. Just like I did in the past, I'm just going to create a big system. The big system is composed of 4 rows and 4 columns. So it is 1, 2, 3, and 4. 1, 2, 3, and 4. Now this system is filled with zeros. So you have 0, 0, 0, 0, 0, 0, 0, 0. And then 0, 0, 0, 0. I'm going to write the stiffness matrix for each one of these elements. So for the first spring, we have 1000 minus 1000. I remember you have the stiffness for the spring to be K minus K minus K and K. So for the first spring, you have the 1000 is the stiffness. So this is 1000. 1000. If you look into the second spring, this is 2000. And just to not have to write down all these zeros, what I'm going to do, I'm just going to take the 3 zeros outside. I'm just going to write this as 1 multiplied with 1000. So it is 1000 multiplied by 1 minus 1 minus 1 and 1. The second spring is 2000 multiplied by 1 minus 1 minus 1 and 1, and then 3000 multiplied by the same. So it's 3000 multiplied by 1 minus 1 minus 1 and 1. Now I want to find the relation between these global and local systems. If you look into the first element, this is node number 1 and this is node number 2. 1 is related to 1, 2 is related to 2. So 1 and 2 are going to be 1 and 2, 1 and 2. If we look into the second one now, again, second spring, you have node number 1 and node number 2. This is 1 first column and 2 second column, 1 and 2. This is linked to 2 and 3. So I'm just going to write 2 and 3 on top of that. 2, 3, 2, and 3. And if you look into the last one, you have node 3 and 4 connected to 1 and 2. So 1 is linked to 3 and 2 is connected to 4. I'm just going to write it as 3 and 4, 3 and 4. Now, if you want to do the assembly, you go 1, 1, 1, 1, and you have 1000 in there. Now, I want to put the 1000 outside. This is not going to be possible because I have 2000 on this outside and 3000 on this outside. I need to take one number as a common factor between all the 3 matrices. I can't take the 1000 as the common factor. I just delete this one and this one and write here 1000 and 1000. And instead of ones here, I would have 2. And instead of ones here, I would have 3s. So this will be 2 minus 2 minus 2 and 2, 3 minus 3 minus 3 and 3. All right, so this way I can write the 1000 here. And then when I want to add or assemble or just combine these matrices, I can combine them just as 1s and 2s and 3s. All right, so 1 and 1 will result into 1 here. If you look into the second entry is 2 and 1. So I'm just going to do the 4 entries. It's going to be -1, -1, and 1. I am done with the first spring. The second one is 2, 2, and I have 2 in there. So this is 2 and 2. And if you look into this one, you'll find this is the coordinates for 2 and 2. I already have 1 in there, so I will add 2 on top of that. And then I have -2, -2, and +2. So I'll just write them down. I'll write these as 3. And then if you look into the last one, you have a 3 and 3, 3 here and 3 here. So this is added to 3. And then you have -3, 3, and 3. I'm just going to write them down in there. Oops, I just removed this guy here as well. So there I will have a 3 + 2, 5, -3, -3, and 3 positive. Now this is the stiffness matrix. I'll need to write down the displacement and the forces, the relation between both. I just remove these numbers. I don't need them anymore. So I will write U1, U2, U3, and U4 here. And then this is equal to the forces. I'll again remove these from here. I just don't need them any longer. Oops. So this is equal to the forces, which are going to be F1, F2, F3, and F4. Now I get to the boundary conditions, which was the question at the start of the lecture. So first of all, what displacements do I know in this case? Yes, so I know the displacement at this first node. I know this is equal to 0. We use a different color for that. So I know this is 0. And then the last one, I also know that this is fixed. So this would also be a 0. And then for the forces, I know this F1 is equal to the reaction, F4 is equal to the reaction. I don't know them, but I know that at F2, I don't have any force. And at F3, I have 5,000. So I'm just going to replace the ones that I know. 0 here, and then 5,000 here. Again, I've got 4 equations with 4 unknowns. I can solve them just in whatever way I want. I'm going to solve them in my own way, which is going to be a reduced system, creating a reduced system. So first of all, I cancel all the rows and columns associated with 0. So I remove this row and this column, and I will do the same thing for the last row, because it is also associated with 0 and the last column. Of course, this will cancel out the unknown displacements. And this way I have only the unknowns to be on the right-hand side. So these are the only unknowns. And on the left-hand side, I have only knowns. I don't have any unknowns. And I said this is a lot easier to program, to write in a computer code. So I'm just going to write down the reduced system here and write it in terms of equations. So for the first equation, I have 0 is equal to 1,000 multiplied by 3 U2, and -2 U3. So this is 3 U2 and -2 U3. And if you look into the second equation, you have 5,000 now. So it is 5,000 equal to 1,000 multiplied by -2 U2 and +5 U3. So it is -2 U2 +5 U3. Now these are 2 equations with 2 unknowns. The only unknowns here are U2 and U3. So I just solve for them. Just to simplify the solution process, I will cancel out this 1000 because I have 0 in there, and I will remove this 1000 with 3 zeros from here, and then I will be left with these equations. I probably just remove these guys here just to make it easier to see. So this is equal to 0. Then this is equal to 5. Oops. All right, to solve them, I just multiply the second equation with 3 over 2 and add it to the first one. So this way I have 3u2 will cancel out with the 3u2 there. So I will have 15 over 2 equal to minus 3u2 plus, so 3 multiplied with 5, this is 15 over 2 u3. So this is the multiplication. I will remove that. So this is the new equation I have. And by adding these two equations, this is going to cancel with this one. So I will have here 15 over 2 is equal to, in order to be able to add 2 to 15 over 2, I will make it 4 over 2. So I will have 0 here, and then 4 negative, 15 positive, I will have plus 11 over 2 u3. The 2 is going to cancel with the 2, and this will give me u3 is equal to 15 over 11. And if you put this back into the first equation, you can get the value of u2. So you have from the first equation, 3u2 is equal to, this is minus 2u3. I'm taking it to this end, so it's going to be 2u3, and u3 is 15 over 11. So if you multiply it, it's going to be 3u2 is equal to 30 over 11, or u2 is equal to 10 over 11. Now, once I have solved for u2 and u3, I'll just bring them back into the original equation and get the values of the remaining unknowns. So I will now use the first equation. The first equation is f1 equal to 1000 multiplied by u1 minus u2, 0 u3, and 0 u4. So if you look into the first equation, the only thing you have from the first equation, this is 0 multiplied with 1 is 0, u2 multiplied with minus 1, and then you have 0 for the rest of it. So f1 is equal to minus 1 u2, obviously multiplied with the 1000. So I'm just going to write it down. f1 is equal to 1000 minus u2. So this is 1000 multiplied by minus 10 over 11, or you just write minus 10,000 over 11. This is the value of f1. Now come to the second equation. For the second equation, you have f4 is equal to 0 multiplied with 0. This is 0. 0 multiplied with u2. This is 0. This is another 0. Minus u3 multiplied with u3. And then 3 multiplied with that 0. So what is left from this equation is only u3 multiplied with minus 3, and obviously multiplied with 1000. So f2 is going to be 1000 multiplied with minus 3 u3, and u3 is 15 over 11. So it is multiplied by 15 divided by 11. And then the answer is going to be f2 is equal to 45,000 divided by 11. Now to check the equilibrium, I have f1 and f2 to be equal to 5,000. I have only one force in there. This is the 5,000 here. And then I have F1 added to F2 is 10,000 plus F1 added to F2 is equal to 10,000 negative added to 45,000 negative. This is negative as well. Divided by 11. So this is minus 55,000 divided by 11. Well, this is minus 5,000. All right. Do you have any other questions? Oh, yes. Yes, it is F1 and F4 here. All right. Now I want you to solve this problem, exact same problem, one more time, but using this numbering of the springs. I'm going to challenge, I mean, this is not just for you to practice the assembly. I want you to kind of be challenged and really think about the assembly. If the springs are ordered, or the numbering is ordered in a sequential way, if you have 1, 2, and 3, 4, is going to be easy to do the assembly. But if you have the numbers to be reordered, so you have the global numbering to be 1, 3, 4, and 2, then in this case, the assembly is not going to be straightforward. You need to think about it. Now, this is very relevant to a situation when we get, I mean, in one dimension, things are very obvious, but once you get into a system of two-dimensional elements, so for example, think about this assembly of elements in 2D, you have a triangulation, and you want to put numbers on there. So you put 1, 2, 3, 4, and then probably should I go for 5 here or 5 here or 5 here or here? I'll probably go here, and then I put 6 here, 7, and then 8. But how about I change the numbering? How about I start from 1 here and then 2 here? Or should I go for 1 here or 1 here? So things are not very obvious once we get into 2D. So the numbering is a complete issue to discuss in two-dimensional and three-dimensional problems. I don't want you to get into this mess in 2 dimensions. I want you to understand it in 1 dimension. All right. This is very important to try and understand it in 1 dimension. This is why I've proposed a different numbering for the nodes. And I want you to solve it with the new numbering. And later we are going to discuss the differences between the first and the second numbering. So when you write the global matrix will always be 1, 2, 3, 4. 1, 2, 3, and 4. All right. You get a new stiffness matrix, it's going to look different, but if you solve the problem, you should get back exactly the same answers. Now, see what I changed in here. I've only changed the numbering. I did not change the physics of the problem. So the answer should always be the same because the problem is always the same. Changing the numbers should not actually change anything. Show you the assembly now. So if you look into the assembly, you'll see that this is column number 1. So for the first element here, you have nodes 1 and 2 linked to 1, 3, 1, and 3. So 1, 1 should be here, and then you have 3, 1 should be here. So this is 3, 1. If you look into 3, 3, 3, 3 should come here. And if you look into 1, 3, it should be here. Now, if you come to the second element you have, this is 2000 obviously now. So it is connected to 3 and 4. If you look into the second element, the second spring is connected to 3 and 4. So you have 3, 4, 3, and 4. And the first entry, which is 2000 in this case, is at 3, 3. So 3, 3 is happening here. Remember, I already have 1000 in there. So 1,000 plus 2,000 is going to be 3,000. If you look into the second entry, it is 4 and 3. So this is 4 and this is 3. So it is minus 2,000. And then you have 3 and 4. This is 3 and this is 4. So I have the minus 2,000 to be inserted here. And then finally, I have the 2,000 at 4 and 4. So I have 2,000 here. Now, if you come to this last element or the last spring, you have the 4 and 4. The first entry, which is 3,000, should come at 4 and 4. So it would come exactly to the same place where I had the 2,000 originally. So 2,000 plus 3,000, this is 5,000. And then I have 2 and 4. This is 2 and this is 4. So this would come here. This is the minus 3,000. And then I have 4 and 2. So this is 4 and this is 2. So I have the minus 3,000 in there. And obviously I have 2 and 2 will come into 2 and 2, though this is the 2 and 2 would come here. Now, if you solve this, you should get back exactly the same answers like before. So try to solve this now. Globally, yes. So this load vector, I'm going to write the load vector. You still have F1, F2, F3, and F4. I mean, we still have this same order. I mean, the first entry in your vector is 1. The second entry is 2. The third entry is 3. I mean, you cannot have the third entry to be 5, right? This is unreasonable. So F1, you go back to the system, and F1 is the force allocated to this node here. Look into F2. F2 will be here. F3 will be the force coming from this node, and F4 is the force coming from this node. So if you actually substitute the numbers, and then you have the 0 values to be at U1 and U2. So if you go back, you see that U1 and U2 are equal to 0. I mean, in this system, you can either solve it by substitution, like Sahil suggested, or just do the reduced system, which is my way of doing it because I think it's easier. So this is equal to 0 and U2 is equal to 0. So I'll just remove the first and the second row and the first and the second column, and I'll be left with the reduced system to solve for U3 and U4. So I get the value of F3 and F4. I know them. F3 is 0 and F4 is 5,000. I solve for U3 and U4. The answers I get are going to be exactly the same like before. Now, obviously, before I had U2 and U3, but now these are called different names. They are called 3 and 4 because I've changed the numbers of them. The original matrix I had, this is the matrix we have from the example. And this is the matrix we created. Probably this is too messy. I'll just write it down. I hope I don't make mistakes in copying it. So the second matrix we have was K equal to 1,000 minus 1,000, 0 and 0, minus 1,000. And then we have plus, I just don't write this plus sign here, is plus 3,000. And then I have minus 2,000. And then we have 0. Next we have 0 here. And then we have minus 2,000. And then we have plus 5,000. minus 3000. And then for the last row, we have 0, 0, minus 3000. And then we have 3000 here. So this is the matrix we have. All right. Now I want you to think in terms, I probably just need to zoom a little bit so you can see the whole thing. Now I want you to think in terms of these two matrices. I'm going to call this one K bar, and I'm going to call this one K. So you have two matrices. You have K and you have K bar. I want you to think, which matrix would you prefer to solve your system with? I mean, which one you would go for if you have to solve this problem, and why would you pick the one you picked? Because of the zeros, it is the case, yes. So if you look into this matrix K, you'll see that all the zeros are happening above this line or below this line. Or below this line here. So if you look into the non-zero entries, the non-zero entries are really clustered close to the diagonal of this matrix. Whereas this one, you have the zeros scattered all over the place. Now, this is important. This pattern is important for two reasons. I mean, the first reason, when we store the stiffness matrix, I mean, we are going to work on a computer and we are going to store the stiffness matrix. So when we store the stiffness matrix, we cannot afford storing all the entries. I mean, if you look into a system of 1 million degrees of freedom, you'll see that you will have 1 million by 1 million memory location to be booked, and we're talking about gigabytes of memory, but you can easily get into situations where you have billions of degrees of freedom, and then we'll be talking, if you want to store or block the entire size of the matrix, you would be talking about terabytes of memory. And this is something you can't, I mean, at the moment, not on a supercomputer, unless you'll be working on a supercomputer, you cannot access terabytes RAM. So this is something we cannot achieve. And whenever we have larger RAM, obviously we can solve bigger problems. So we really want to solve it efficiently. We don't want to waste memory on zeros, because zeros are not going to add any value. I mean, zero, you multiply it with any entry is going to produce a zero. So you don't need to store that. Now, if you look into this problem here, you'll see that this is quite easy to identify the non-zeros. And you can, I mean, usually we store what we call the profile or the skyline profile of the matrix. So you go to the first non-zero entry in each column and store that. So the skyline of this matrix is going to look like this. It's just going to look like stairs. Whereas in this one, this is the first non-zero entry and you store everything beneath that. This is the first non-zero entry and you store everything beneath that. And then instead of going one step lower, you go one step higher. And the skyline here is going to look like this. So it's going to store a lot, or result into storing a lot of zeros that you don't need. And instead of blocking, I don't know, probably 1 gigabyte of RAM, you end up blocking 100 gigabytes of RAM. And this is something you cannot work with. So this is going to result into a lot more operations. It's going to consume a lot more time from the computer to finish the calculations, but it's also going to consume a lot of RAM, and reading and writing into the RAM is becoming the bottleneck. I mean, at the moment, the sort of CPUs we have are really very quick. They only spend time reading and writing into the RAM. This is the bottleneck, basically. So avoiding to read and write into the RAM is going to speed up the code a lot more than just having to deal with a lot of non-necessary operations. So one way to treat this is just to apply permutations. And if you apply permutations, so if you move these rows and columns around, this matrix would still be the same, but you can organize it in such a way so that all the diagonal entries are non-zeros and away from the diagonals are the zeros. I mean, this is something you can do, but it would be a lot easier to choose the right numbering right from the beginning. And in many software at the moment, I mean, if you use Lucis, I think probably Lucis would not offer you that, but in ANSYS, I think you have this capability. You can create the problem, create the mesh, and then ask ANSYS to optimize the numbering. So ANSYS is going to go into the problem and renumber the whole thing in such a way that the zeros are away from the diagonal of the stiffness matrix. All right. Do you have any questions about this example? Okay, so I have a second example. I want you to solve this example yourself, and I'm going to probably show you the solution for this example after week 5. So I'm going to put this system I'm going to put this problem on Canvas so you can go and see it. I want you to think about how to do the assembly in this case. In this case, we have node number 1, and this entire rigid block is node number 2, and then you have node number 3 and node number 4. I want you to think about the assembly of this problem. Again, I'm going to show you the solution in probably 2 weeks' time, but you need to think about it yourself.